Welcome back, students. We are working on the last lesson in our section on Introduction to Derivatives, and this time we'll be looking at some applications of derivatives. And one of the big applications is the use of a derivative to find rate of change of one variable with respect to another. So derivatives can be used to find rates of change, and particularly changes in distance over time. And so you'll find that I'll be referring to position functions, and often they use the names of S of t or X of t as names for position functions. So those will be your original functions. That would be where an object has its position. Sometimes it's its initial position. So using S of t or X of t to name those types of functions. And we're going to look at two types of velocities that we can work with when we know a position function. So the first type of velocity is average velocity. Now, average velocity is more algebraic in nature because it's a velocity that is taken over an interval of time. Now, with velocity, those of you who've been through physics know that velocity is not only measured as a positive number, but also as negative or zero, because velocity not only involves your speed, but also the direction. So it can be a negative, a positive, or a zero. Now, algebraically, the average velocity is nothing more than change in y over change in x, and you would be more familiar with your slope formula, that m equals y2 minus y1 over x2 minus x1. So just calculating the slope. So you would have to know two ordered pairs. Keep in mind that we're really looking at distance over time. And so this would be the algebraic interpretation of finding the average velocity. Graphically, when you find the average velocity, you're finding the slope of the secant line to a function. So if you had a function graphed, such as just a simple parabola, the graphic interpretation of what would be going on here is a secant line. So we would look at what happens as this line goes through 2 points of your original position function. And then the formula that we'll be using, and really it's nothing more than doing the slope, but using the function notation, using often S of t. On a time interval from A to B, you could calculate the average velocity by doing S of B minus S of A over B minus A. But I don't want you to be intimidated by that. Your A and B are simply X values. They're a point in time. So, for example, on this graph, this X value for the ordered pair on our secant line would be A, and then the X value for the other ordered pair on your secant line would be B. So those are your X values in the ordered pairs, and S of B and S of A are simply the Y values of those ordered pairs. So finding the average velocity amounts to plugging in your x values to the position function and then calculating the slope of that secant line. For calculus purposes, though, we can do more with less information. And so we don't need to know an interval of time. We can actually find the velocity called instantaneous velocity at a particular time. So in algebra, you have to know an interval of time. With calculus, you don't need an interval. You can find the velocity at a certain point in time, and that's called instantaneous velocity. Now, the algebraic interpretation of this is that you would be doing the limit as your time, your change in time, so delta t approaches 0. So the limit as your change in time approaches 0 of s of t plus delta t minus s of t all over that change in time delta t. And that hopefully looks familiar to you because that is the definition of the derivative. And so that would let you find the velocity at a certain instant in time. The graphical interpretation is that you have the slope of the tangent line to a graph of a function. So rather than needing 2 points, you could actually just find the tangent line, so going through 1 point and using that 1 point to calculate the slope of the tangent line. Well, fortunately for you, you no longer need to use the limit definition of a derivative because you know the power rule. So the formula that you'll be using to calculate instantaneous velocity, first of all, we'll call it v of t. So we'll actually call it a function, v of t, and it is simply the derivative of the position function. So we can actually put that in the algebraic interpretation. I just didn't want you to think you had to do the limit definition, but what I described in that algebraic interpretation is actually s prime of t. It's just that now you can do the power rule and not have to do that limit definition. So the instantaneous velocity is found simply by doing the derivative. And then if you have a time, you can plug that in to the derivative. So there's your introduction to the notation. And we'll do another video for the backside, which is your example of this type of application.